Hey, hello, it's Ranjan. Welcome back to my YouTube channel. And today I will talk about object detection algorithm. And this would be first video of object detection playlist. And as of now, these days, object detection algorithms is getting used extensively in every field now. And we can detect almost any object or from the given image or video or real-time movements, and we can detect any type of the object to the very minute details such as brand name of the car or a logo on the car, or we can detect anything. And the interesting thing is that there are many pre-trained models which are available in the internet, so we don't need to train each and every category of the object, and that model we can use by some lines of code. And I would be showing you each and everything in this playlist, and it's all possible due to the deep learning or the availability of the computation resources as of now. And I will be showing this implementation of such object detection in my third or fourth video. So in this video I will go through the foundation of the object detection, the basics of the object detection. I will be showing you what is the difference between traditional object detection which we used earlier like 5 or 6 years back, and now what we are using now these days, and what are the different stages in the object detection, how we trained, and what are the some known state of the art models or pre-trained model that we are using, or we can say transfer learning. I will be show you some models and what are the known data sets on which these pre-trained models are trained on, and how we evaluate performance, whether our model is detecting fine or not. And if you already know about the bit 10 pieces and every basic of the object detection, you may skip this video. I will be uploading another video for you guys in 2 or 3 days. You may refer that video for more advanced object detection. So let's start this video. And one more thing, if you don't know about the deep learning, just have a look on these videos that I have uploaded for deep learning. So in this playlist, I have uploaded what is deep learning, how it works, and what are the neural network, what are the types of the neural network. And second important thing, you should know about CNN, because object detection works on these two pillars, CNN and deep learning. So let's start this video without wasting any further time. So what is image processing? What we can do with the image processing by processing image? First of all, we can classify the image, whether the given image is of which type. Suppose we can classify this image is cat, this is dog. So this is the first thing that we can do with image processing. So it's very easy in case of deep learning or machine learning, because it is just to classify. It's the case of only two images. It would be very quick to train on these 2 or 3 or 4 images, but so it can detect. We will give some images of the cat and model will detect, yeah, this type of the images similar to the cat, so this is cat. And second important thing is object classification and localization. So what is localization? If you will see in this image, it's there would be more background, but we have to detect in which part of the image our object is. So this red line is localization, because if you will see, there is no cat, there is no cat, so this image is getting localized. So this is object classification and localization. So this is the type of a object detection. We can't say in this is a detecting a dog. It is classifying this image into dog, but it is not detecting where the dog is, because dog is here. So this is bounding box. If you have seen in this image, you would be seeing a bounding box. So this is a bounding box, and here we have a percentage. This percentage confidence score. So this is object detection. It is not classification, because it is detecting every object and it is localizing that object. So here it's the same. So this is object classification and localization. And third thing is, when we have a multiple objects in a single image, so we have to detect each and every object, and we have to localize that object in which part of the image we have a object. So if you will see here, we have dog, cat and duck. So it has localized that frame. So here we have dog, here we have cat, here we have another cat, and here we have duck. So it has been classified and localized, and we have multiple objects. So these are the three important things that we can do with image processing. And it's not about only image processing, we can do with video processing. In the real-time video, or we have a downloaded video, we can run the model on our video and it will detect which type of object it is. So earlier, what object detection we are using, because earlier we don't had much GPU resources and computational resources, so we were not using deep learning, we was using machine learning at that time. So earlier, the pipeline of the traditional object detection models has been divided into three stages. So first stage was information region selection. Informative region selection was that suppose we have a different objects in any position of the image. So we have image and we have different objects and in different region in the given image, and it could be having different size. Suppose here is a small dog, here is a big dog, and here a image of dog is there, and it could be different aspect ratio or different size. So we have to scan the whole image with a multi-scale sliding window. So earlier we were using a sliding window. I will show you. In first stage we were using sliding window. So how was that? So suppose this is a window and we have selected this size of the window. So what we will do, we will slide this window to next level here, and it will be, so here my window has been slided to the right. In the next level it would be slided to this level. So we have to slide over windows to complete image, but this would be very exhaustive strategy to find out all the possible positions of the object, because what we are doing, we are capturing each and every part of the image by sliding. So obviously it will take computational resources, it would be very exhaustive because it would be having a large number of windows. If we can do some customization, we can select fixed number of windows, but if we are selecting some fixed number of windows, suppose we have an image and we are selecting only 6 windows, so that would give us unsatisfactory regions because we may miss some more important regions. And once we have the selected some regions here, then we apply feature extraction. And as of now, these days we are using CNN to do feature extraction, but at that time we were not using CNN. So what we are doing, we were manually extracting features. So we have to recognize different objects that we have captured here. We need to extract visual features from the image, which will provide a semantic and robust representation that object is this. But due to the diversity, there are many appearance, illuminations, lighting conditions or background, it was very difficult to design a robust model. And once we have a feature, whether we were extracting manually or automatically by computer, then we were applying classification. So classification was that logistic regression, or it could be support vector machine, or would be ADA boost, adaptive boosting. So this was complete machine learning. In this classification we were doing machine learning. And the example of the traditional object detection, we have already seen HAR features. I have uploaded one video of computer vision using HAR cascade features. If you have not watched this video, you can watch this video. Here's a link. And we have histogram of oriented gradients. I will show you. So this was a histogram of gradient orientation. What we are doing, suppose we have this image and we are applying histogram of gradient orientation and we are detecting some graphical representation. So in this graph you will see like this is representing a human like structure, so it will detect this is a human. So now I will show you what object detection that we are using now. So basically we have two types of object detection as of now these days. First is region proposal based. In this, if you will see, we have RCNN, faster RCNN, fast RCNN, and FCN, FPN, or mask RCNN. So these all type of region proposal based, and this is regression classification based, multi-box attention net, YOLO, SSD. This type has three stages, and it would be of one stage. It would be of single step. It would be done in single step. So first we will talk about region proposal based frameworks. In this we have three things. First is region proposal generation. Second is feature extraction with CNN. And third thing, classification and bounding box regression. If you will see, it is pretty same as we do in traditional object detection. But in this, we are using region proposal generation instead of information region selection, in which we were using sliding window. But in this, we are not using sliding window. And in second step, in that we were using feature extraction with machine learning. But in this, we are using feature extraction with CNN. If you don't know about the CNN, you may watch this video. I have uploaded a video with a clearly explanation of CNN. So basically, CNN is a convolution neural network, and it's a neural network that has a special layer which is convolution layer or some pooling layers. And third is classification and bounding box regression. So bounding box I have already shown you in the first video, a video with a object detection, in which we have a green color box. We say that as a bounding box. I will be showing you further videos. So regression, because it will calculate the exact plot of the bounding box, and classification, it will classify which type of category it is. So, and these three models usually trained separately. We have to separately train these three models. So basically it has three models. So first I will tell you what is region proposal generation. These types of algorithm adopt selective search. Selective search is a very important term, because in selective search what it will do, suppose we have this type of image, it will divide this image into segment. Now this image is having a number of segments. Every block is a separate region. So we are just generating a region here. So basically selective search method, it's algorithm that relies on simple bottom up grouping. So next would be feature extraction. So feature extraction is to just collect the features, and that features we will provide to our last layer as we do in CNN. So in this stage, each region that we have generated here, it would be cropped into fixed resolution. So just to extract the important features. So next we would be having a classification. So classification, in this we will be using some classification algorithm, because we would be having some pre-trained category. So we would use linear support vector machine, or we can use adaptive boosting for classification. So I will be showing you all these things in my next slides. So now we have regression classification based framework. If you will see in this framework, we were training three separate models. So basically it would be more time taking, so efforts would be more, and the time spent in the handling different components, it would be become the bottleneck in real time application, because real time application should be very quick. So that's why we have designed in a framework which would be completed in one step only, and it would be based on global regression and classification. What it will do, it will just map straightly from the image pixels to bounding box coordinates and class probability. So it will reduce the time it is taking. So basically it has combined all three things in one step only. So what it will do, it will just map straightly from the image pixel, these are the pixel, and it will just convert to into bounding box. And we have two significant frameworks which we are using as of now. One is YOLO, you only look once, because it would be in one step, and second is single shot detector. So in this video, at this point, I have covered how was object detection earlier when there was no deep learning, and how object detection is now, and how it detects object. In the next video, I will show you couple of pre-trained models, how they works, and then we will discuss some known dataset on which pre-trained models are trained on. Then we will see some annotations tools, then we will see application. So that's all in this video. So I believe you are interested to see more explanation about this topic. So if yes, let me know by posting the comment. I am giving my 100% to explain this topic. Do let me know if I'm lacking somewhere or I'm missing something. To support my channel by subscribing this, and hit a like button on this video if you think it's really helping you. So see you all in the next video. Till then, goodbye, enjoy, happy learning, keep rocking.
This is a cat. You know that. Everyone watching this video knows that. Even a toddler will point to this photo and call it a cat. Well, not necessarily. Sometimes children mix up cats and dogs, especially if they weren't exposed to different breeds or colors or sizes of animals before. But as soon as they've seen enough cats and dogs and other furry friends, they've learned the difference. We apply similar logic when helping machines understand the visual world. This technology helps autonomous vehicles avoid pedestrians and other cars, as well as react to road signs. And that's how computer models can locate tumors in MRI images with up to 90% accuracy. The image recognition skill allows computers to process more information than the human eye, often faster and more accurately, or simply when people are not involved in looking. So, how can machines see and interpret the visual world? Well, let's talk about computer vision and its applications. In the first 3 years of our lives, we create 1 million neural connections per second. Whenever we learn something new, a neuron in our brain lights up with an electrical impulse and sends the message about a new experience to other neurons, forming connections. Everything we know is shaped by these neural connections, networks of them. Whenever we see a new type of cat, the same connection strengthens, making it easier for us to recognize an animal as a cat next time. With machines, we use similar neural networks, but those networks are artificial. Just a disclaimer, we will be using simplified explanations and formulas to make concepts more digestible. An artificial neural network is an advanced machine learning algorithm that can answer questions without any hints from humans. Questions like, how much will it cost to fix a car or a roof after the disaster? Tractable uses AI to study the photos taken by insurance clients to evaluate how much should be reimbursed. And in this demo, NVIDIA applies image recognition to satellite imagery to detect destruction of homes in the Woolsey fire in 2018. The neural network looks for specific features that it knows must represent damage, and it does so by doing math. A neural net consists of many layers: an input layer that receives the data, the output layer that makes the final forecast, and the hidden layers, where the magic happens. Layers consist of nodes, neurons, that are all interconnected. Each neuron is performing a computation. Just like biological neurons receive signals about the world, artificial ones receive data. The difference? It's represented in a format understood by computers, numbers. For images, it's the color values of the pixels composing the image. Neurons in the input layer are not that important because they simply receive data and pass it on. So let's focus on this node in one of the hidden layers. Connected to many nodes in the previous layer, it accepts one number from each node. But it doesn't treat all these connections equally. They have different importance, or weights, also represented as numbers. The higher the weight, the more influence one node has on another. So a node multiplies inputs by their corresponding weights and then adds them all up to create a single number. This number will become an input for the nodes in the next layer. So the weights basically help the net look for the data that carries the greatest importance for the task, and layer upon layer recognize more of the details until the last node puts it all together and says, here are all the areas hit by hail. Yes, an experienced evaluator can also do this kind of job manually, but they will have to travel to the affected zone and inspect large areas, immensely extending the claim processing time. But a computer can analyze data from photos without workers moving around and wasting precious time. Of course, it doesn't have to be just static images. Amazon incorporated neural networks to develop one of its most groundbreaking products, Amazon Go stores. Every part of their unique just walk out experience is run by computer vision. Cameras and sensors keep track of every person entering the store and what they're doing, whether picking up an item or returning it to the shelf. At the same time, every product sold at the store is tracked by cameras too. Is it on the shelf or in someone's hand? And finally, those two instances are combined to answer the ultimate question: which person took what product? With almost 30 locations in the US and now a shop in London, the automated stores are no longer a concept but the retail reality, as Amazon starts providing the technology to Whole Foods, Tesco, and Starbucks. This way, computer vision is transforming the way offline shopping works. Any visual data that can provide useful information can be processed by machines, saving time, money, and providing competitive advantage. This was the basic principle that all neural nets work by, but they can be different too. For image recognition tasks, convolutional neural networks are used the most. They were specifically created to work with two-dimensional image data and are extremely good at locating important features of objects. Here's how convolutional neural networks work. Computers see images as grids of pixels. As you may know, each pixel is represented and encoded as a combination of red, green, and blue of different intensity. Here's what a computer sees when you input this picture. Let's switch it to grayscale and reduce the resolution for simplicity. From this color intensity map alone, the computer must determine how many cars are parked in the parking lot. This information can be used to optimize price or redirect traffic to less populated areas. This will get a bit math heavy, so be prepared. In a convolutional neural network, we do almost the same thing the normal neural network does, but instead of multiplying one pixel value by its weight, we multiply a patch of pixels by a set of weights called a filter or a kernel. This is done because, in images, the difference between neighboring pixel values is important. Pixels with low values are darker, while high values are lighter. If the contrasting pixels are located close together, it's a good indication that we're looking at an object's outline. So, we multiply this patch of pixels by the filter and receive 1 pixel. The filter moves across the image patch by patch until it transforms the whole picture, so the convolutional neural net not only extracts value from the image, but also reduces its dimension, making it easier to process. Depending on what features we want the machine to find, we apply a specific filter. They're like templates helping bring out needed features. This one can pinpoint the outlines. Other kernels can filter out horizontal or vertical lines. There are kernels for finding faces and separate face features. Okay, but how does a computer know which weights to multiply by? We're glad you're catching on, because this is kind of a crucial part. Neural networks learn those weights during the training process. Want to know how to train a deep learning model? Let's start with something familiar. How do humans see? Well, to be honest, we don't know for sure how our brains apply meaning to the visuals around us. The most popular theory is pattern recognition. It states that we rely on patterns, or features, to figure out what objects we're seeing. A cat has its set of characteristics, a long tail, fur, and big pointy ears to start with. But we don't teach our children about cats by listing all those characteristics to them. We show them pictures because it's easier and allows for much more flexibility. This and this are both cats, even though they're different in many ways. But a child is capable of catching all the things, features that are common in them. So we do the same thing with machines. We show them pictures, tell them what's in them, and hope they figure out all the important features by themselves. Say you want to build an app that will calculate the probability of pneumonia from X-ray images, similar to the one we prototyped for decision-making in the hospital setting. As we already established, you can't simply tell the computer what disease looks like on a radiograph. Moreover, you want to distinguish between different conditions. So the best approach is to give the computer a vast amount of labeled chest X-rays to extract valuable features on its own. This is one of over 112,000 training images we use for our pneumonia scenario. Its pixel map is fed to the input layer, which performs convolution. Except this time, all filter values are random, completely incidental. The results are passed to outgoing layers, where they're multiplied and added many times before arriving at the output layer. There, the resulting output is compared to the desired one. In case of an error, the system starts tweaking weights over and over until it gives a correct result. The process of training is basically finding appropriate weights from the constant feedback loop. This video might not look like much, but here, an aerospace manufacturer, Airbus, is making aviation history. In this demonstration, they present a new autonomous technology that will soon assist pilots of commercial flights in taxiing, takeoffs, and landings. Notice the pilot nervously hovering a hand over the stick while the aircraft soars into the sky on its own accord? Airbus uses cameras, sensors, and software powered by computer vision to let the jet navigate the runway independently and take off at the appropriate time. In harsh weather conditions, pilots will have to manually correct the plane. But in ideal circumstances like this, they can delegate such operations to the computer and get busy with navigational tasks and communication. On the ground, the transformation promises to be even more drastic. Currently, over 6,000 pedestrians die in traffic accidents every year in the US, a number that increased by almost 50% since 2010. Over 90% of collisions happen due to drivers getting distracted. But if we remove human error from the equation, we can significantly improve road safety. In the first quarter of 2021, Tesla vehicles operating with autopilot became engaged in a single road accident for every 4.19 million miles driven. In the same period, Tesla cars not using autopilot experienced one accident for every 978,000 miles traveled. So, it seems like self-driving Tesla cars can be 4 times safer than the ones operated by a regular human driver. Even though people are wary of autonomous cars, stats speak for themselves. Tireless and watchful, autopilots are projected to make roads safer and more walkable as we inevitably move towards the autonomous future. One of the most popular uses of computer vision is facial recognition. The unique architecture of our faces allows machines to perform fantastically accurate face matching to validate our identity or find missing persons. Since the launch of their facial recognition system in 2016, Interpol identified almost 1,500 terrorists, criminals, persons of interest, and missing people. These applications are our triumph in a decades-long effort to make computers see the same way we do. That said, it's not always that positive. It's one thing when technology tracks humans on the road, but a completely different one when it recognizes their identities, logs details about their personal lives, or classifies marginalized groups to mistreat them. Deepfakes can be entertaining in one context, while harmful and destructive in others. Shockingly accurate face search engines are available both to those who want to stop misuse of their pictures and to those who want to stalk other people. This is a common dilemma that almost every technology becomes subject to. Should we stall the progress to protect our privacy? It seems that computer vision has advanced too far and promises too many benefits to have us ever choose to stop progress in its tracks. Our job here is to provide regulations and rules to make sure that progress and ethics go hand in hand.
Challenge and future directions. Despite the significant progress made in object recognition, several challenges remain and there are various areas for future research and improvement. Number 1. Occlusion and clutter. One of the major challenges in object recognition is handling occlusion and clutter in real-world scenarios. Objects can be partially occluded by the other object or obscured by various environment factors, making it difficult to accurately detect and recognize them. Viewpoint and pose variations. Object recognition algorithms need to be robust and variations in viewpoint and pose, as objects can appear differently depending on the angle from which they are observed. This particularly challenge for deformable objects or with complex 3D structures. Number 3. Scalability and efficiency. As object recognition systems are deployed in real-world application, there is need for scalable and efficient algorithm that can process large amounts of data in real time. Huang 2017, Howard 2017. This is crucial for applications such as autonomous vehicle where rapid and accurate object recognition is essential for safe navigation. 4. Domain adoption and generalization. Many object recognition algorithms are trained on specific datasets and may not generalize well to new domains or environments with different characteristics. Feng et al. 2018, Ganin and Lemtsky 2015. Developing technique for effective domain adoption and improving the generalization capabilities of object recognition models is an important area for research. 5. Explainability and interpretability. As object recognition systems become more complex and are used in critical applications, there is growing need for explainable and interpretable models. Celia Raju 2017, Ribeiro et al. 2016. This involves developing techniques that can provide insights into the decision-making process and the reasoning behind the model's predictions. Number 6. Multimodal object recognition. While most object recognition research has focused on visual data, there is increasing interest in multimodal object recognition, which combines information for multiple sensor modalities such as vision, depth and audio. This can lead to more robust and accurate object recognition system, particularly in challenging environment. Number 7. Few-shot and zero-shot learning. Traditional object recognition models require large amount of labeled data for training, which can be consuming and expensive to occur. Few-shot and zero-shot learning techniques aim to develop models that can recognize new object categories with minimal or no labeled examples, leveraging knowledge from previously learned categories. Adversarial robustness. Object recognition models can be vulnerable to adversarial attacks, where carefully crafted perturbation or noise can cause the model to misclassify objects. Developing robust and secure object recognition systems that are resilient to adversarial attack is an important research area. Number 9. Ethical considerations. As object recognition technology becomes more prevalent and applied in various domains, there is a need to consider the ethical implication and potential bases that may arise. These include adhering issues related to privacy, fairness, and accountability, particularly in application involving sensitive data or decision-making process that can impact individuals or communities. This challenge and future direction highlights the ongoing research efforts and the multidisciplinary nature of object recognition in artificial intelligence. Addressing these challenges will require advancement in areas such as computer vision, machine learning, computational resources, and ethical consideration to develop more robust, efficiency, and trustworthy object recognition system. Conclusion: object recognition in artificial intelligence is a fundamental and rapidly evolving field that plays a crucial role in enabling intelligent systems to perceive and understand their surroundings. This technology has numerous applications across various domains including autonomous vehicle, robotics, surveillance system, augmented reality, medical imaging, and many others. This research paper has provided a comprehensive overview of object recognition covering its fundamental concepts, techniques, algorithms, and types. It has explored how object recognition works, from data acquisition and preprocessing to future extraction, object representation, classification, and localization. The paper has also discussed the various types of object recognition including instance recognition, category recognition, semantic segmentation, object detection, and instance segmentation, each unique application and techniques. While significant progress has been made in object the paper has several challenges remain. Examples, including occlusion and clutter in action, viewpoint and post variation, scalability, application in domain adoption and generalization, autonomous vehicle, explainability, and retail and inventory management, medical imaging, robotics, and industrial challenges and robustness and ethical considerations. In areas such as computer vision, machine learning, computational resource, and ethical consideration, interdisciplinary collaboration and holistic approach will be essential in developing more robust, efficiency, and trustworthy object recognition system. As artificial intelligence and computer vision technologies continue to evolve, object recognition will play increasingly important role in enabling intelligent systems to seamlessly interact with the physical world. By covering the remaining challenges and advancing this field, we can unlock new possibilities and applications that will have profound impact on various industries and aspects of our lives.